Imagine waking up tomorrow and finding out that time travel isn't just a fantasy from science fiction, but a real possibility grounded in the laws of physics. What would you do? Would you visit the past to witness the birth of the universe, or leap into the future to see how humanity evolves? The idea of time travel has fascinated us for generations, inspiring countless books, movies, and late-night debates. But what if I told you that the secret behind time travel isn't just a product of wild imagination, but something that science has been quietly unraveling for over a century? Today, we're going to peel back the layers of myth and speculation and reveal the real science behind time travel. What's possible, what's impossible, and what might be just around the corner. Let's start with the basics. When most people think of time travel, they picture a machine, a DeLorean, a blue police box, a spinning vortex that whisks you away to another era. But before we can talk about machines, we need to understand what time actually is. Time feels so familiar, so obvious, that we rarely stop to question it. We measure it with clocks, we schedule our lives around it, we feel its passage in our bones. But what is time really? Is it a river flowing from past to future? Is it a dimension like space that we move through? Or is it something even stranger? For centuries, time was seen as absolute, a universal clock ticking away the moments, the same for everyone, everywhere. This was the view of Isaac Newton, whose laws of motion and gravity shaped our understanding of the universe for over 200 years. In Newton's world, time marched forward relentlessly, unaffected by anything that happened in the universe. But in the early 20th century, a young patent clerk named Albert Einstein shattered that view forever. Einstein's theory of relativity revealed that time is not absolute. It's flexible, malleable, woven together with space into a four-dimensional fabric called space-time. According to relativity, time can speed up or slow down depending on how fast you're moving or how close you are to a massive object. This isn't just a theoretical idea. It's been confirmed by countless experiments. Astronauts on the International Space Station age ever so slightly slower than people on Earth because they're moving faster and are farther from the planet's gravity. GPS satellites have to account for these effects, or their navigation systems would quickly drift out of sync. This phenomenon is called time dilation, and it's the first real clue that time travel, at least to the future, isn't just possible. It's already happening. If you could travel close to the speed of light, time for you would slow down dramatically compared to people back on Earth. You could take a journey to a distant star, traveling for what feels like a few years, and return to find that decades or even centuries have passed on Earth. This is known as the twin paradox, and it's a direct consequence of Einstein's equations. In a sense, astronauts are already time travelers, moving ever so slightly into the future with every orbit. But what about traveling to the past? This is where things get tricky. The laws of physics, as we currently understand them, don't forbid time travel to the past outright, but they do make it incredibly difficult. One of the most intriguing possibilities comes from the concept of closed time-like curves, or CTCs. These are paths through space-time that loop back on themselves, allowing an object or a person to return to an earlier point in time. The idea was first explored by mathematician Kurt Gödel, who found a solution to Einstein's equations that allowed for such loops. Later, physicist Kip Thorne and others showed that certain kinds of wormholes, tunnels through space-time, could, in theory, be used to create CTCs and enable time travel to the past. Wormholes are a staple of science fiction, but they're also a legitimate solution to the equations of general relativity. Imagine space-time as a sheet of paper. If you fold the paper and poke a hole through it, you create a shortcut, a wormhole that connects two distant points. If you could stabilize a wormhole and manipulate its ends, you might be able to create a time machine. For example, if one end of the wormhole is accelerated to near the speed of light and then brought back, time dilation would cause less time to pass at that end compared to the other. Step through the wormhole, and you could emerge in the past. Of course, there are enormous challenges. Wormholes, if they exist, would be incredibly unstable, prone to collapse the instant anything tries to pass through. To keep a wormhole open, you'd need exotic matter with negative energy, a substance that has never been observed in nature. Even if you could find or create such matter, the energy requirements would be astronomical, far beyond anything humanity can currently achieve. And then there are the paradoxes. The paradoxes. Time travel to the past opens a Pandora's box of logical problems. The most famous is the grandfather paradox. What happens if you travel back in time and prevent your own grandfather from meeting your grandmother? Would you cease to exist? If so, who went back in time to cause the change? These kinds of paradoxes have led some physicists to speculate that the universe has built-in safeguards, mechanisms that prevent paradoxes from occurring, perhaps by making such events impossible or by branching reality into parallel timelines. This brings us to the many worlds interpretation of quantum mechanics. According to this idea, every time a quantum event has multiple possible outcomes, the universe splits into parallel branches, each realizing one outcome. If time travel to the past is possible, perhaps it doesn't change your own timeline, but creates a new branch, a parallel universe where the past is different, but your original timeline remains intact. In this view, time travel doesn't rewrite history. It creates new histories. Let's keep going, because the deeper you look, the more fascinating and perplexing the science of time travel becomes. We've already seen that relativity allows for time dilation, and that wormholes and closed time-like curves are mathematically possible, at least on paper. But what about the real universe? Are there any hints in nature that time travel could actually happen, or is it all just theoretical speculation? To answer that, we need to look at the universe's most extreme environments, black holes. These cosmic monsters are regions where gravity is so intense that nothing, not even light, can escape. At the heart of a black hole lies a singularity, a point where the known laws of physics break down. But around the singularity, space-time is warped to an incredible degree. Some solutions to Einstein's equations suggest that rotating black holes, called Kerr black holes, could contain ring singularities that might, in theory, allow for closed, time-like curves. In other words, if you could survive the journey, which, let's be honest, you probably couldn't, you might be able to loop back in time by traveling through the warped space-time near a rotating black hole. But before you start packing your bags for a trip to the nearest black hole, there are some serious caveats. First, the tidal forces near a singularity would rip apart any object long before it could complete a time loop. Second, even if closed time-like curves exist in the math, it's not clear they exist in the real universe. Many physicists believe that some as yet undiscovered law of quantum gravity would prevent time travel to the past, preserving causality and keeping the universe safe from paradoxes. Still, the fact that the equations allow for such possibilities is both tantalizing and unsettling. It suggests that our understanding of time is incomplete, and that the universe may be stranger than we can imagine. But let's not get lost in the math. Let's bring things back to Earth and ask, what does all this mean for us? Is time travel just a theoretical curiosity, or could it have real-world implications? One area where the science of time travel is already making an impact is in the field of quantum information. Quantum entanglement, a phenomenon where two particles become linked so that the state of one instantly affects the state of the other, no matter how far apart they are, has led to the development of quantum teleportation. While this isn't time travel in the traditional sense, it does challenge our notions of space and time, and it's paving the way for new technologies like quantum computers and ultra-secure communication networks. But perhaps the most profound implication of time travel research is what it tells us about the nature of reality itself. Time, as we experience it, seems to flow in one direction, from past to future. This is known as the arrow of time, and it's closely tied to the concept of entropy. According to the second law of thermodynamics, entropy, a measure of disorder, always increases in a closed system. This gives time its direction, its irreversibility. You can scramble an egg, but you can't unscramble it. You can remember the past, but not the future. Yet the fundamental laws of physics are time symmetric. The equations work just as well if you run them backward as forward. So why do we experience time as a one-way street. This is one of the deepest mysteries in science, and it's directly connected to the question of time travel. If the laws of physics don't care about the direction of time, why do we? Some physicists believe the answer lies in the initial conditions of the universe. The low entropy state at the Big Bang set the arrow of time in motion, and everything since has been a consequence of that original asymmetry. This brings us to another fascinating idea, the block universe. According to this view, past, present, and future all exist simultaneously in a four-dimensional space-time block. Time doesn't flow. Instead, every moment is fixed, like frames in a film reel. Our consciousness moves through these frames, giving us the illusion of passage. In the block universe, time travel is just a matter of moving to a different location in space-time. This idea is supported by relativity, which shows that different observers can disagree about the order of events, depending on their motion and position in the universe. But if the block universe is real, what does that mean for free will? If the future is already written, are our choices just illusions? Or is there room for genuine novelty and creativity in a universe where every moment is predetermined? These are not just philosophical questions. They're at the heart of the science of time. The more we learn about time, the more we realize how much we don't know. Let's not forget the practical side of time travel. While building a time machine may be out of reach for now, the principles of time dilation are already being used in technology. As mentioned earlier, GPS satellites have to account for both special and general relativity to provide accurate positioning. Without these corrections, your phone's map would quickly become useless. In particle accelerators, scientists routinely accelerate particles to speeds where time dilation becomes significant, allowing them to study processes that would otherwise be invisible. So where does this leave us? Time travel, as depicted in movies and novels, remains a dream. But the science behind it is real, and it's reshaping our understanding of the universe. The secrets of time are being revealed, one experiment, one equation, one insight at a time. And as we continue to probe the mysteries of time, we may find that the line between science fiction and science fact is thinner than we ever imagined.